In this video, we're going to talk about some of the basic terms in geometry. So in the top picture, we have two endpoints, and that tells us that we have a line segment here. We name a line segment by any 2 points that are on that line segment. So I could call this line segment AB. We put a little bar on top to indicate that we're talking about a line segment. We could also call it line segment BA. The order of the points does not matter when we're talking about a line segment. Here we have a ray, and the question here says, what is the difference between the line segment and the ray? Notice how the line segment has two endpoints, but the ray only has one endpoint and has an arrow on the other side. The arrow indicates that the ray goes on forever in that direction. So if this is point A, and let me call this point B, a good name for this ray would be ray AB. Now the question is, can we also call this ray BA? And the answer is no. The reason why we cannot call this ray BA is because rays do have direction. The arrow indicates the direction that the ray is extending infinitely in. So here, this ray is starting at point A and it's going infinitely in the direction of point B towards the arrow. So the arrow on top needs to point towards B. So this would not be a correct name for the ray. How does a line differ from a ray? You might see that a line has arrows on both ends. That means it extends infinitely in both directions. If this is point A and this is point B, we could name this line AB or line BA. And there's an infinite number of points on the line, but just like with a line segment, we name a line with 2 points. Any 2 points that are on that line can be used to name that line. Remember the notation when you're talking about different geometric objects, it's very important. So make sure you are using the correct notation for whatever object you are talking about. Over here, we have a congruent statement, and we need to complete it with either an equal sign or a congruent symbol. Congruence, or when two figures are congruent, means that they are exactly the same. The same size, the same shape, the same measurements, exactly the same. And our congruent symbol looks like this, the equal sign with the squiggly on top. Here in the first picture, I do see a congruence mark on both of the line segments, and I do see the bar on top of AB and PQ letting me know I'm talking about the line segments. So here I'm going to put a congruent symbol because we're talking about the line segments themselves. This says line segment AB is congruent to line segment PQ. We use congruence when we're talking about the line segments as a whole. If we jump to the third one over here, it looks almost identical to the first one, except if you take a look at the congruent statement, there is no bar on top. When there's no bar on top, we're still talking about a line segment, as you can see from the picture. We're just talking about the measurement of the line segment. So here, instead of reading this as line segment AB is congruent to line segment PQ, we can read this as the measurement of AB is equal to the measurement of PQ. When we're talking about the objects themselves, we use congruence. When we're talking about the measurements, we use equality. Here, we're talking about the triangles themselves, triangle ABC and triangle DEF. So I'm going to use a congruent symbol. We're not specifically talking about measurements, we're talking about the whole objects themselves. Here we have a line segment, and it gives us the length of GH2. And the question is, what is the missing piece if the whole line segment GI is 7? The answer is 5. You might be thinking, that's easy. We get 5 because 2 plus 5 makes the whole 7, and that's absolutely right. When we have a line segment that's split into parts and we want to get the whole thing, all we have to do is add those parts together to get the whole. And that is the partition postulate. Remember, a postulate is just any rule in geometry, anything that we accept as true in geometry. And the partition postulate says the sum of the parts equals the whole. Over here, before we do more examples with the partition postulate, just one more new vocabulary word. Here we're told that AB bisects CD at point E. The word bisect means to split into two equal or congruent parts. Let me write that here. Bisect means to split into two congruent parts. So here, CD is the line segment that's getting bisected. AB is bisecting CD, so AB is doing the bisecting, but CD is the one that's actually getting bisected. Since CD is getting bisected, it's being split into two equal parts. So we know that this half of CD, CE, and this half of CD, DE, are equal to each other. I'm going to put a congruence mark on each piece to let me know that they're congruent to each other. So a conclusion that I can draw here is that CE is congruent to DE. We can also say that E is the midpoint of CD. A midpoint is the halfway point of the line segment. It's the point where it splits into those two congruent parts. So E is the midpoint of CD because it's the point that's splitting it equally on both sides. Okay, here we need to find the value of x. And I notice that we're given this piece over here, AB, this piece over here, BC, and we're given the length of the whole line segment as 15. Using the partition postulate, we can say that if we take both of the parts and add them together, we get the whole. So 2x minus 17 plus negative 8 plus 2x is equal to 15. Take a second, combine your like terms, and solve for x. And here we have that x is equal to 10. Over here, we're told that TV, which is this whole line segment here, is 14x minus 8. And we need to find the length of TU. So we need to find the length of this piece of the line segment. Since we know both pieces, 9x plus 2 and 5, and we know the whole is 14x minus 8, I'm going to make an equation that says if I take one piece, which is TU, and I add the other piece, which is UV, I get the whole line segment, which is TV, or 14x minus 8. Let's take a second and solve for x. And here we have x is equal to 3. But make sure you read the question carefully. Here the question is not asking you for the x value. The question is asking you to find the length of TU. TU is represented as 9x plus 2. So we actually have to take our x value and substitute it into 9x plus 2 to see what it is. So we have 9 times 3 plus 2. That's 27 plus 2, which is 29. So 29 is the actual length of TU. Here we're told that Q is the midpoint of line segment PR. Since Q is the midpoint, we know it's the halfway point exactly in the middle of the line segment. It's the point that splits the line segment into the two congruent parts. So since we know that this half PQ is congruent to this half QR, we can set them equal to each other because they have the same measurement. So we can say 7x minus 16 is equal to 4x plus 2. Let's take a second and solve for x. And here we have that x is equal to 6. In this question, it was just asking for the x value, so we don't have to plug into anything. We are done. Here we are being asked if each of the geometric objects can be bisected. So let's start with the line segment. We know a line segment can be bisected. We can find the midpoint. For example, if this whole line segment is 8, we can find the midpoint, the point that splits the line segment equally in half. So we can definitely bisect the line segment. If you can find the midpoint, you can bisect the line segment because a bisector needs to pass through that midpoint because it cuts it equally in half. So we can definitely bisect a line segment. Can we bisect a line? The answer is no. The reason is because a line goes infinitely in both directions. That's what the arrows indicate. Since it goes infinitely in both directions, we can't measure a line. It has infinite length. So we actually can't find the midpoint. So we can't bisect the line because we can't find the spot to go exactly in the middle because it has infinite length. Using that same idea, we can't bisect a ray either. Even though a ray does have an endpoint on one end, it has an arrow on the other end, so it does extend infinitely in one direction. Since it's going forever in one direction, our ray does also have infinite length, so we can't find that midpoint. We can't find the point to bisect it at so that it's split equally in half. We can bisect an angle. That's because an angle, even though it's made of two rays, does have a measurement. For example, this angle might be a 30-degree angle. So we can bisect it by splitting it in half, which would be into two 15-degree angles. Since angles do have measurement, we can bisect an angle. Here we have points A, B, and C that are collinear. Collinear means that the points are on the same line. And it does tell us that point B is between A and C. So I'm going to draw a picture representing the situation. Point B is between points A and C. Now be careful here. It does not say that B is the midpoint of this line segment. It doesn't say that it's equally in between A and C. It just says between. Nothing about congruent, nothing about equal, nothing about midpoint. So we can't assume that this half and this half are equal. What we do know is that AC, which is the whole thing, is 3x plus 3. AB is negative 1 plus 2x. And BC is 11. We can make an equation like we were doing for the other examples by saying if we take the parts and add them together, we get the whole line segment. One part is negative 1 plus 2x, plus the other part, which is 11, equals to the whole thing, which is 3x plus 3. Let's take a second and solve for x. And here we have that x is equal to 7. The next thing we're going to talk about is something called the addition postulate of congruence. What the addition postulate of congruence says is that if you start off with two congruent objects, in this case line segments, and to each one you add on something congruent, your result, your sum, will also be congruent. So notice how here in this example, we're starting off with two congruent line segments, AB and CD. Here they have measurements, they are both length 8. They're congruent because they're exactly the same. They both have the same measurement. And to each of these line segments, we're going to add the same line segment EF, which has a length of 3. So notice this was line segment AB, and we just stuck EF onto the end of it. This was line segment CD, and we just stuck EF onto the end of it. Both of these original line segments were length 8. AB and CD were both length 8, and EF was length 3. So both of these new line segments that we just created are both length 11. So they're congruent to each other. Once again, if you start with two congruent line segments and to each one you add on a congruent line segment, your resulting line segment, the sum of the line segments, will also be congruent. That's the addition postulate of congruence. Let's look at an example over here. In this situation, we were given that AB is congruent to DC. And we're trying to reach the conclusion that AC is congruent to DB. Here's AC. Notice how AC is longer than AB. Here's DB. Notice how DB is longer than DC. So the information that we're given, the line segments that we're starting with from the givens, are shorter than the ones that we need to end up with. That tells us we're going to need to do addition because we need to take our short line segments and we need to make them longer. And we usually make things bigger by adding in math. Let's start with making line segment AC. So we're given line segment AB and we need to get to line segment AC. To get from AB to AC, we need to add on BC. I'm going to write that down. AB plus BC makes AC. Now let's talk about making DB. We're starting with information about line segment DC, and we need to get DB. What we can stick onto DC to make DB is CB. I'm going to write that down as well. DC plus CB makes DB. Notice the two line segments that we're starting with, AB and DC, are congruent to each other. And we know for sure that they're congruent to each other because that was the given information that we started with, the information that was marked in the diagram. We're also adding on something congruent to each one. BC is congruent to CB. The reason for that is because it is the same segment. Notice how it's the same two letters, BC and CB. If we look at the diagram, BC and CB are talking about the exact same segment. Notice how they're both highlighted in the it's highlighted in the two colors here because it's the same segment. Whenever we have something that's the same as itself, we can say it's congruent to itself by the reflexive property. I'm going to write that here. The reflexive property says anything is congruent to itself. So that justifies why BC and CB are congruent, because anything is congruent to itself by the reflexive property. Since we're starting with congruent and adding on congruent to each one, the end result will be congruent. So we do know for sure that AC will be congruent to DB due to the addition postulate. We also do have the subtraction postulate of congruence, and that's the opposite. Instead of starting with information that's too small and needing to make it bigger, we would use the subtraction postulate when we're starting with information that's too big and we need to make it smaller. If you take a look at this example, notice we're starting with information about line segment MP and line segment NQ being congruent to each other. And we want to arrive at the conclusion that MN is congruent to PQ. The information that we're starting with, MP, is longer than MN, which is what we need to end up with. And the information that we're starting with, NQ, is longer than PQ, which is what we want to end up with. Since we're starting with longer segments than what we need, and we need to make them shorter, we're going to be doing subtraction because subtraction takes away the parts of things that we don't need. It helps us to remove stuff that we don't want. That's subtraction. Subtraction follows the same rules as the addition postulate. You need to start with congruent and subtract congruent in order to end up with congruent. So here, if we're starting with MP, but we just want MN, we would need to get rid of NP. I'm going to write that here. MN minus NP. Oops, I just wrote that incorrectly. MP, that's the segment we're starting with, the long segment MP. Take away NP, this piece, leaves us with MN, which is what we want. And on the other side, we're starting with NQ. But we don't want NQ. We want to end up with PQ. So to just have PQ, we need to get rid of NP, and then we'll just be left over with PQ. Notice how we're starting with two congruent segments. We know that MP and NQ, the two long segments that we need to make smaller, are congruent because that was given to us. And notice how we're subtracting something congruent from each one. NP is congruent to NP because of the reflexive property. Anything is congruent to itself. Since we're starting with congruent and subtracting congruent, the differences that we get, MN and PQ, will also for sure be congruent to each other. We're going to end here with what is the difference between the partition postulate and the addition postulate of congruence. You might want to pause the video so you can think about that question for a minute. So the partition postulate, and I'll just abbreviate that, partition postulate, says that the sum of the parts equals to the whole. So basically, the partition postulate is if you have one line segment that's broken into different parts, what it says is that if you take all the parts and add them together, you'll get the whole line segment. So this is an example over here. If we take all the pieces of this piece, this piece, this piece, and this piece, and we put them all together, we get the whole entire line segment AE. So it's when you're starting with one line segment or angle. It could also apply to angles, even though we haven't really seen angles yet. When you have one object that's broken into parts, and you need to add all the parts up to get the whole thing. The addition postulate is when you're starting with two separate objects to begin with that are congruent. You're starting with two congruent objects, and to each of those, you're adding on something congruent. Like our example that we saw, where this piece was 8 and this piece was 3. So the sum, the whole new line segments created, needed to also be congruent to each other because we're starting with congruent, and to each congruent line segment, we're adding on something congruent. So the result, the sum, when you add the parts together, needs to be congruent. So the main difference is the partition postulate is talking about one object that's divided into pieces, while the addition postulate is talking about two separate objects that are congruent, that are each getting something congruent added onto it.